In the previous videos, we have covered grouping models into subsystems and adding OpCom blocks to facilitate communication between subsystems. Now that we have covered subsystems and communication, we are ready to learn about maximizing parallel execution. Using more cores on a simulator does not necessarily improve the performance of a simulation if the model is not properly parallelized. The first concept we must understand is the notion of a state. Without digging into the mathematics for now, a Simulink block that has a state is a block whose output depends on something that happened in the past. For instance, a delay block introduces a state because its output is computed from a preceding input. An integrator is also another example. A trick to spot blocks that contain a state is that they usually have an initial condition field, since there would otherwise be no existing data to input at the very beginning of the simulation. On the contrary, a block like a gain does not have a state because its output at any step depends on the input of the same step. It is simply feeding the value through. Let's look at some examples to clarify this notion. Here, we have an example where a model is divided into two computation subsystems. However, this case will not execute because both subsystems are waiting for information from the other subsystem before performing their own computations. This is called deadlock. Here, to improve our previous example, we have added an integrator block to introduce a state. This is unfortunately not enough, as we now have serial execution occurring. What happens here is that the SS subsystem will send a value to the SM subsystem. The SM subsystem will perform its computation, and only afterwards will it send its results to the SS subsystem. The computation of the SS subsystem will occur subsequently. Here, we are missing out on fully parallel execution because the result of SM subsystem is a constraint on the calculation of SS subsystem. So, we do not run both calculations at the same time. Further improving on our previous example, we have added an integrator block into the SM subsystem, placing an integrator block in each one of our subsystems. However, there's a gain block placed after the integrator block. Let's see why this is not optimal. At each step, the calculations will occur as follows. The SS subsystem will send the result to the SM subsystem. The gain will be computed as a separate step in the SM subsystem, and the result of this gain will be sent to the SS subsystem. Finally, both subsystems will be calculated. We can see here that by placing the gain after our state-producing block, the gain gives us an extra manipulation in our calculation. Finally, we can look at our best-case scenario. Here, we're going to have a fully parallel execution. This is because at each step, RT-Lab will do the following. First, it will communicate the results between each subsystem. Then, it will do the computation of both subsystems at the same time, truly in parallel. To summarize, in order to achieve optimal parallel execution, it is important that the last block of each subsystem has a state, such as a memory block or an integrator block. Then, at the beginning of the next time step, the data will be readily available to be transferred to the other subsystem.